Hi, my name is Brad Zelafro, and today I'll be discussing the ECE561 final project, Remote Assistive Integrated Network. In this project, I was responsible for developing the entire smartphone application, as well as the Bluetooth detection application that's featured on the smartwatch, which will be discussed in length in the following presentation. Now, I don't know if you know any loved ones who have been personally affected by Alzheimer's or dementia, but if you do, then you'll probably recognize that the burden undergone by the caregiver is just as great, if not greater, than that felt by the patient. I was my own grandfather's primary caregiver for over 2 years, and every day was a constant struggle to make sure his needs were met. And my grandfather and I are in no way alone in this scenario, with approximately 46.8 million people living with dementia worldwide. And as the global population increases, this number is expected to increase to 131.5 million people by the year 2050. Now, with the prevalence of this disease comes a significant financial burden, with $818 billion being spent in 2015, and as the numbers of those who suffer from this rise, this will rise in kind, with a projected $2 trillion being spent in the year 2030. Now, we all have a fairly good understanding of what people who suffer from Alzheimer's encounter, but let's go ahead and clearly delineate the problem we're trying to solve. We know they have memory lapses. We know they have difficulty concentrating and planning sequences of tasks. They have trouble organizing themselves, and they easily become disoriented in both time and space throughout the day. Now let's quickly touch upon the burden felt by the caregiver. In a survey that was completed in 2014, 60% of respondents who were the primary caregiver of Alzheimer's patients claimed that fulfilling their duties resulted in them having very high stress. And that's where our solution, RAIN, comes in. RAIN is a dynamic hybrid assisted living platform that allows caregivers to issue time and vicinity-based personalized messages and interpret the behavior of their loved ones through real-time feedback. Now let's go ahead and take a look at the high-level functionality that we would like this solution to implement. No one's in a better position to understand the particular difficulties of an Alzheimer's patient than their loved one. So imagine if a loved one could go throughout their home, identify regions in that home that they know the patient has difficulty interacting with, and leave audio instructions that would be played aloud when the patient approaches them. And that's precisely the kind of functionality that RAIN affords caregivers and patients. Here we see a high-level schematic that connects the caregiver with a smartphone to a patient that's equipped with a Bluetooth-capable smartwatch, and we can see the communication channel that exists between them. Now let's go ahead and take an in-depth look at each of these stages to see precisely how data is transmitted to the patient and back. It begins with the smartphone application used by the caregiver. Here we see the 4 primary activities, each of which will be explored throughout this presentation. But we'll begin the process with tag association. Tag association allows the caregiver to use a built-in QR code scanner to capture the unique MAC address of a Bluetooth module that is provided to them. Once they scan this MAC address, they then provide a name indicating where this will be placed throughout the home. Once that's done, they go to the audio record activity, select that name from a drop-down menu, and choose the time during which they would like this instruction to be issued, either morning, noon, afternoon, night, or all day. They then select whether this is a prompt asking the patient if they need help, or an instruction which actually delivers the help. You can see there's a dynamic animation letting the caregiver know they're recording, and then they can stop and submit the recording to the servers. Now, once this is done, the relevant data pertaining to this audio file is encoded in the name of the file in the following format. The location, the type of instruction, whether a prompt or an instruction, and the time it's meant to be played are delineated using underscores. So for the example on the right, where we have a kitchen prompt issued in the morning, that will become kitchen underscore prompt underscore 0.3gp, as you can see from the table below, which serves to translate between the times and their aliases. Next, my colleague Kunal will explain how this information is conducted to the smartwatch worn by the patient and how feedback is generated and given back to the caregiver.
My name is Kunal, and I'll be talking about the server, database, and different feedback functionalities implemented in this project. Basically, my contribution to this project was to develop the Python TCP/IP-based servers, MySQL database, and client application installed on the patient's watch. We have created Python TCP/IP-based servers which establish two-way connections, that is between the caregiver's application on smartphone and the patient's application running on the smartwatch. These two applications then pass the data into the intermediate database. As you can see that the instructions recorded by the caregiver are passed to the patient's watch using Python TCP/IP sockets. Later, when the patient responds to these prompts recorded by the caregiver, the log for these responses is sent back to the caregiver's application on the mobile phone. This process basically helps the caretaker to monitor the activities of the patients even remotely. So we have multiple Python servers running concurrently on our local systems. These servers are used to send or receive the audio instructions or prompt recorded by the caregiver for a particular QR code to the database. Now let's take a look at how this process works. Once the caregiver registers a tag and records the instruction, he needs to press the submit button, upon which a TCP socket is created and the audio file saved in the format mentioned by Brad earlier is then uploaded to the central server. The server receives the information from the caregiver's phone in the format that includes the location of the beacon, the type of the audio, and the time span for which the recording is available. It could be morning, afternoon, night, or all day. The database then maps these received information packets to a new format that includes a MAC address, the type of instruction, and the time span that is recognized by the smartwatch. At this stage of prototype development, we have used XTouch Watch, which is a full-fledged Android-based system. The primary reason we chose this watch is the fact that it always acts as a Bluetooth master, allowing us to scan multiple beacons simultaneously. We have these custom designed beacons which are placed at different locations, and the watch identifies them based on their MAC addresses. Now we will see the reverse of the process that I just talked about. The log of the activities that have taken place on the watch will then be sent back to the database in predefined format. This format consists of MAC address followed by the type of instruction, the time at which the instruction was played, and the date. The caregiver's application then queries the database, which in turn generates a log based on the activities of the patient. This log will then help the caregiver to monitor the patient activity in timely manner. There are two possible ways the caretaker can monitor the activities of the patients. First, the current or the live activities can be tracked using this option of live activity. We have a SQL database on the online server that currently retrieves the log of the patient activities. Information about the date, time, the type of audio, the location based on the MAC of the beacon. This information is stored on the online server for further interpretation and analytical processes. As you can see, the live activity log provides a detail of the location at which the patient has been to, the response whether the instruction was accepted by the patient, the date, and the time at which this activity took place. The other possible option to track the activity is to see the log for a specific date. This is sort of a history that database keeps track of. Now let's just do some cost analysis. The three major competitive technologies which focus on specific domains like communication, monitoring, and pill regulation, when consolidated, would cost around $550. Our solution offers more functionalities with much cheaper cost than the ones offered by the competitive technologies discussed in the previous slides. Let's take a look at the areas where we could improve. The prototype currently implements all the functionality we have described so far. However, we see many opportunities to improve this solution further. By embedding microcontroller in each Bluetooth beacons, we could intuitively communicate with the caregiver the optimal distance that should exist between each beacon through red and green LED lights. We would also like to establish more reliable patient monitoring facility. When the watch is stationary or is being removed from the patient, the caregiver will get an alert message after a particular time. This time can be configured by the caregiver using the Android application on the phone. We also plan on developing pill monitoring activity that allows for more fine-grained scheduling of tasks to closely regulate the schedule with which the patients take their medication. We can obviously reduce the cost of the application by replacing numerous of Bluetooth beacons with triangulation scheme. Finally, the battery life can be improved by replacing HC06 module with BLE modules, which would double their lifespan. Now we'll see the live demonstration of the functionality of this application.
Alright, so now we'll do a brief demonstration exploring all the functionality that was discussed in the preceding presentation. It'll start by taking one of the unique Bluetooth beacons, using the tag association function of the application, using the built-in QR code scanner to conveniently capture the MAC address that will allow us to integrate this beacon into the system. Right, there we go, we've caught the MAC address. And now we'll give it a name representative of where it will be placed in the home. We'll call this kitchen, and I spelled kitchen with a J. All right. Now we'll go ahead and go to the audio record activity. We'll select kitchen from the menu. I'll go ahead and make this an all-day prompt. And now I'll record a prompt asking the patient if they need help. Do you need help in the kitchen, Grandpa? Okay, now we'll take a look at the servers. You can see we have an active connection to the smartwatch. Now I will send the audio file right here, and this will indicate the number of packets being received by the watch. So that is submitted. And we can see it has sent 5 packets containing the entire 3GP. Now I'll record an instruction the same way I did the prompt. Instruction. Now I'll tell him what he can do in the kitchen. There's pizza in the refrigerator. Right? Now we'll submit that just like we did the prompt. Great. Now we'll turn on one of the Bluetooth beacons, and I am equipped with the smartwatch that is currently polling the RSSI of various Bluetooth signals. Once it detects RSSI above a certain threshold for this beacon, it'll play those instructions aloud. Now we've set the threshold relatively low so the instructions can be heard as we approach the beacon. Okay, so now the beacon is on as indicated by the light. I will now come in. Do you need help in the kitchen, Grandpa? All right. Do you need help in the kitchen, Grandpa? I will say yes. There's pizza in the refrigerator. There's pizza in the refrigerator. Great. Okay. Now, once that is done, live feedback was instantaneously generated. I can go to the monitor activity. I can do the live feedback to retrieve those recent activities. Kitchen, kitchen, oops. Kitchen and kitchen. Now I will go to the calendar history, and I can retrieve all the activities that have occurred on this date. Okay, we'll retrieve that log. This is a larger file, so it takes a little bit more time to process. There we go. And you can see right there the most recent activity that occurred. Would actually be at the bottom right here.